Good afternoon, class. We are looking at section 5.7, inverse and radical functions. In this section, we cover inverses and radical functions. The objectives are find the inverse of an invertible polynomial function, restrict the domain to find the inverse of a polynomial function. Summary of polynomial function. As you recall, polynomial functions are in the form of f of x equals a sub n x to the power of n plus a sub n minus 1 x to the power of n minus 1 all the way to a sub 0. A sub n, the leading coefficient can't be 0. N is a whole number. And by whole number, w representing the whole number, we mean 0, 1, 2 to infinity. The domain is all real numbers. The degree of a polynomial function is n. Graph is smooth and continuous. Maximum number of turning points is n minus 1. At the 0 of even multiplicity, the graph touches the x-axis, can't cross. At the 0 of odd multiplicity, the graph crosses the x-axis. Between zeros, the graph of f of x is either above or below the x-axis. And as far as the end behavior is concerned, for large absolute value of x, that means x goes to negative or positive infinity, the graph of f of x behaves like the graph of y equals a sub n x to the power of n, meaning its leading term. A polynomial of degree 1, p of x equals mx plus b, is simply a linear function y equals mx plus b. A polynomial of degree 2, as an example, p of x equals x squared plus bx plus c, is a quadratic function. As you recall, the vertex is located at x equals minus b over 2a, and if you plug in f of minus b over 2a, gives you the y coordinate of the vertex. Real zeros of polynomial functions, we have n of x over d of x equals q of x plus r of x divided by d of x. That's the algorithm for division. We can write n of x as the product of q of x and d of x plus r of x. Dividend equals quotient times divisor plus remainder. The remainder theorem indicates if we are dividing f of x by x minus c, the remainder is simply evaluate the function at c, f of c. The factor theorem says when you evaluate it, if the remainder is 0, then x minus c is a factor of the function f of x. The intermediate value theorem, or short IVT, says if f of x is a polynomial function or any continuous function, and if for real numbers a and b, the values f of a and f of b are opposite in sign, then there exists at least one real zero between a and b. So f of a is, for example, negative, f of b is positive, and 0 is in between. For a continuous function, it has to cross the x-axis, or it must have a 0. Number of zeros theorem. A function defined by a polynomial of degree n has at most n distinct or unique complex zeros. The rational zero theorem indicates if f of x is the following polynomial, a sub n x to the power of n all the way to a sub 1 x plus a sub 0, then factors of a sub 0 over factors of a sub n. Fundamental theorem of algebra says if p of x is a polynomial of degree 1 or more, then there is some number k such that p of k equals 0. Therefore, p of x becomes x minus k times q of x, where q of x can also be factored, resulting in the following having n roots or factors. Conjugate zeros theorem indicates if p of x defines a polynomial function having only real coefficients, and if r equals a plus bi is a zero of p of x, then its conjugate, or bar a minus bi, is also a zero of p of x. Odd degree polynomials, therefore, have at least one real zero, since complex conjugate zeros happen in pair. Rational functions. A function f is a rational function if f of x is n of x over d of x, and d of x can't be 0, where n and d are polynomials. The numerator and the denominator must be polynomials. The domain of f consists of all real numbers except the zeros of the denominator of f of x, which is d of x. So the domain is all real numbers except what makes d of x 0. Rational function in lowest term. After we put it in lowest term, if there's a common factor, we drop from the top and the bottom. Then VA, short for vertical asymptote, you set d of x equal to 0 to find it. Finding horizontal and oblique asymptote of a rational function. If the numerator has a degree n, so a sub n x to the power of n all the way to a sub 0, we call it n of x, and the denominator d of x is b sub m x to the power of m all the way to b sub 0, so it has a degree m. If n is less than m, horizontal asymptote, HA, short for horizontal asymptote, y equals 0. If n is equal to m, then the leading coefficients take over. A sub y equals a sub n over b sub n. If the difference is precisely 1, that means the degree of the numerator is larger than the degree of the denominator by precisely 1, then we do long division or synthetic division. It results in mx plus b and a remainder. Y equals mx plus b is oblique asymptote, also known as slant asymptote. Oblique asymptote, also known as slant asymptote. That's the synopsis of what we've covered. And now 5.7, inverses and radical functions. Function, as you recall, for each x in the domain of f, there is exactly one image f of x in the range. However, an element in the range can result from more than one x in the domain. To determine whether a function is one-to-one, here's the definition. A function is one-to-one if each element in the range corresponds to exactly one element in the domain. Or a function f is one-to-one if for any two numbers a and b in its domain, if f of a equals f of b, that means a must be equal to b. And when a is not equal to b, f of a cannot be equal to f of b. Or when x sub 1 is not equal to x sub 2, f of x sub 1 cannot equal f of x sub 2. Let's look at a simple example. Determine whether a function is one-to-one. If you look at this one, it represents a one-to-one function because for every element in the domain, there is precisely one element in the range. For this one, the answer is no. Why is that? Because x sub 1 corresponds to y sub 1. Also, x sub 2 corresponds to y sub 1. In essence, the range is being repeated. So a function x can't be repeated. A one-to-one function y can't be repeated. Any of them that repeats, it fails to be a one-to-one function because y is repeating, right? X sub 1, y sub 1, x sub 2, y sub 1. Look at this. This means this pair, x sub 1, y sub 1. And this means this pair, x sub 2, y sub 1, it fails to be a one-to-one function. And the next one, it's not even a function because x sub 1, y sub 1, x sub 1, y sub 2. So the domain is being repeated. So it's not a function. So x sub 1, y sub 1, x sub 1, y sub 2. That's the reason it's not a function. Let me just write that. So this means x sub 1, y sub 1. This means x sub 1, y sub 2. It fails to be a function. So the x being repeated. In this case, the answer is no, because now we have 55, 38 as a pair, 61, 38, and therefore it's not a one-to-one function. In other words, in order for it to be a one-to-one function, the x and y coordinates cannot repeat. So the last one, this is -2, this is -1, this is 0, 1, 2. All the x coordinates are different. Let's write the domain. So if I were to write the domain, I would say domain -2, -1, 0, 1, 2. And if I were to write the range, 6, 3, 2, 5, 8, they are all different. Therefore, yes, it makes it a one-to-one function. One-to-one function, HLT, horizontal line test, if a horizontal line can be drawn so that it intersects the graph of a function at more than one point, the graph is not a one-to-one function. No horizontal line can intersect the graph more than once. For example, right here, you see this horizontal line crosses the graph at 2 points. Therefore, it fails to be a one-to-one function. Is this a function? Yes. Is this a one-to-one function? No. How do you make it one-to-one? You can restrict the domain, for example, here from 0 to infinity, and now it becomes a one-to-one function. So is the function yes, one-to-one no? Restriction can make it work. Monotonic functions are one-to-one functions. So what are monotonic functions? Monotonic function is either increasing or decreasing on an interval. In the entire interval, it's increasing or decreasing. So if we have a one-to-one function, when x sub 1 is not equal to x sub 2, f of x sub 1 can't be equal to f of x sub 2. Not one-to-one, if f of x sub 1 equals f of x sub 2, then x sub 1 is not equal to x sub 2. This is another way of looking at it. Both of them result in the same concept. Now, for each function, use the graph to determine whether the function is one-to-one. Very simple function, y equals x squared. Everybody knows how to graph it. All you have to do, draw any horizontal line. You can see clearly crosses the graph. Y equals 1 crosses the graph more than once, and therefore it fails to be a one-to-one function. Because it fails a horizontal line test, it's not a one-to-one function. On the other hand, y equals x cubed, you know how to graph it. You cannot come up with any horizontal line that crosses the graph more than once, and therefore it makes it a one-to-one function. So this fails HLT, this does not. This is not a one-to-one function, this one is. Inverse of a function defined by a map or a set of ordered pairs. So as f takes us from the domain to range of this function, f inverse, this is read f inverse, brings us back. If f of x is a one-to-one function with ordered pairs of the form x comma y, the inverse function f inverse of x. This is read f inverse. is a one-to-one function with ordered pairs of the form y comma x. Suppose that f is a one-to-one function. Then corresponding to each x in the domain of f, there is exactly one y in the range because f is a function. And corresponding to each y in the range of f, there is exactly one x in the domain because f is one-to-one. The correspondence between the range of f back to the domain of f is called the inverse function of f. The symbol f inverse is used to denote the inverse function of f. In other words, if we want to define f inverse of x with the pair b comma a, such that, this is read such that a comma b is an element of f of x. Again, this is read such that, this one is read such that, and this is read an element of. Domain of f is range of f inverse. Range of f is domain of f inverse. The domain and range are interchanged. Given the function f of x 1 comma 4 2 0 3 7 minus 2 1 minus 1 minus 5 5, find the inverse function. All you have to do, interchange x and y. For example, this becomes 4 1. This becomes 0 2 all the way to the end. So f inverse 4 1 0 2 7 3 1 negative 2 negative 5 negative 1. Now, if we were to graph this 1 4 and then 4 1 2 0 0 2 3 7 7 3, they look like this. I'm assuming everybody can plot pairs. So if we plot those, for example, 1 4 is here, 4 1 is here. 2 0 is here, 0 2 is here. 3 7 is here, 7 3 is here. And you do all of those pairs, you notice that ordered pairs in function f of x, we are using the blue and red one for f inverse. And you notice points for the two functions are symmetric with respect to the line y equals x. Verifying inverse functions, where g of x is x cubed, we want to verify g inverse of x is cube root of x. For any one-to-one function f of x and its inverse f inverse of x. F of f inverse of x is x, f inverse of x is x. X in the domain of f inverse in this case, x is in the domain of f of x. So in other words, their composite function must be x. So let's look at the composite function of these two, g of g inverse of x. That means replace this x with this g inverse of x is this one. As you can see clearly, cube root of x to the third power is x. That's very simple. Now, g inverse of g of x, which means we are going to replace this x with x cubed. And cube root of x cubed obviously is x. So that is simple to verify. We proved, because we verified the inverse function. By the way, As long as one of them works, the other one works. You don't have to necessarily show both, but we are doing it for practice. And as long as one of them works, they are inverse of each other. Now let's look at f of x equals 2x plus 3. F inverse of x is half of x minus 3. Let's prove that they are inverse. So let's look at f of inverse, or f of f inverse of x, which means if you look at this function, you're going to replace this x with f inverse half of x minus 3. And clearly, 2 and 1/2 cancel each other. You get x minus 3 plus 3, which is x. So that's done. However, let's look at the second one. Let's look at f inverse of f of x, which means in this function, we're going to replace the x with 2x plus 3. So half of x is replaced with 2x plus 3. And we notice these two cancel each other. Half times 2x gives you x, and we are done. Pretty straightforward, everybody. We're going to continue with the different sets of functions. F of x is 3 over x plus 5, and f inverse is 3 over x minus 5. For what values of x is f inverse of f of x equals x? For what values of x is f of f inverse of x equals x? It's important to know when they ask you this question, you look at this function. Look at the inner piece and see where this one is defined. So I'm looking at this one and say this is defined everywhere except at x equals -5. In other words, I'm going to set the denominator equal to 0 and x becomes -5, and I exclude that. So this one, x can't be -5. But for this one, I look at f inverse of x. I have to look at this. And this one, when I look at it, says x can't be 0. So I'm going to write, for what values of x is f inverse of f of x, domain of f, domain of f, x can't be -5. For what values of x is f of f inverse equals x, this time domain of g, f inverse, I should say. Maybe I should write f inverse instead of that. Let's do this. Let's change this to f inverse. Okay, because normally we use f and g, so that's why I use that, but f inverse. So I hope everybody's clear on that. And so let's work on this. F inverse of f of x. You just plug in. You are going to replace, we go to f inverse of x, you're going to replace this x with 3 over x plus 5. So we are going to write this function, and we're going to replace the x with f of x. Now, right? 3 times x plus 5. You multiply the extremes. You make the numerator into a fraction, 3 over 1. 3 over 1, this is 3 over 1. And then 1 times 3, you multiply the means. And these two cancel each other. You get x plus 5 minus 5, which is x, and x can't be negative 5. So we looked at the first case. Let's look at the second case, f of f inverse, which means here's now the f function. We're going to replace this x with 3 over x minus 5. So what happens? 3 over x, and again, complex fraction, this is 3x. This is 1 times 3, and the answer is x. And of course, x can't be 0. X can't be 0 because of this. Graphing the inverse functions. As it was mentioned, here's a theorem. Graph of the inverse functions f of x and f inverse of x are symmetric with respect to the line y equals x. That is extremely important to understand. So when we graph it, if if you have a pair a comma b, corresponding to a comma b, we have b comma a. And here's the line y equals x. And the proof is very simple. Y equals x, you know the slope is 1. So I'm going to give you an idea how to do that, and you can prove it on your own. So this one has the slope 1. And if you have two pairs, these two, you should be able to calculate the slope and then come up with the equation of a line and find the slope. Obviously becomes the negative reciprocal of that, which is -1, which makes it a 90-degree angle. That means the two lines, if you continue indefinitely, they are perpendicular. So the reason I want you to see this is a 90-degree angle. So you can calculate the slope easily. And then all you have to do, find the point of intersection between these two lines, which is this point. And then this distance, you have to show this distance using the distance formula is equal to this distance, which is easy to show. And again, finding this. In any event, so if you want to graph using this concept, just pick a few pairs, and there you have it. For example, here, a sub 1, b sub 1 corresponds to b sub 1, a sub 1. So how do we graph this? Let's do exactly the same thing here. How do we do that? -2, -1 corresponds to -1, -2. -1, 0. 0, -1. 2, 1. 1, 2. So first, understand that, and all you have to do, plot those pairs. For example, and this is comma. Okay. For example, we have a -1 -2, 0, -1, 1, 2, and we connect them, and it looks like that. This has 2 line segments. This has 2 line segments. What's important to understand, if the 2 functions that are inverse ever intersect, the point of intersection takes place on the line y equals x because their x and y are interchangeable. So this point must have an x and y for this that is the same as this one yx in essence because you're changing it. So the x and y for this one, that's why the only way for it to work, x equals y. Finding inverse functions, only one-to-one functions have inverse functions. The domain of f of x is the range of f inverse. The range of f of x is the domain of f inverse. The graphs of f of x and f inverse are symmetric about the line y equals x when graphed on the same axis. To find the inverse function of a one-to-one function, first, remember, this is important, this -1 here in this is not an exponent. It is read f inverse. We've mentioned that. I just thought it's worth mentioning it again, okay? So we want to make sure that we don't make that mistake, okay? Now, here's the process. Number 1, replace f of x with y. The reason we do that because it makes it easier to work. Number 2, interchange the 2 variables x and y. And right at this step, we do have the inverse. However, we normally solve for y. And finally, we give it a name, f inverse. That's the idea, everybody. We want to find the inverse of f of x, which is 2x plus 3, and graph the 2 functions, f as well as f inverse. Number 1, we're going to call this y because it makes it easier to work with. Number 2, we are going to interchange x and y. So this becomes x, this becomes y. Therefore, we have x equals 2y plus 3. And number 3, we want to solve for y. That means we are going to move the 3, we make it x minus 3. And now we're going to divide both sides by 2. So y becomes half of the right side. Y becomes half of x minus 3. Now, give it a name f inverse. So therefore, f inverse of x is 1/2 x minus 3. Let's check. To check, we have to find a composite function, either f or f inverse or f inverse of f. You don't have to do both. One is enough. But for the sake of argument, we're going to do both for this example. So if we want to go with f or f inverse, we are going to replace this x with f inverse, y or f inverse. So replace this x with half of x minus 3. When we do that, these two cancel each other. We get x minus 3 plus 3, which is x. Now we're done. We don't have to do f inverse of, but it's a good practice to do so, which means for f inverse of, we're going to replace this x with 2x plus 3. When we do that, these two cancel each other, and 1/2 times 2x results in x. So we prove that we are not wrong. Now, let's graph the two lines. Those are easy. Let's find a couple of pairs. This one clearly has the y-intercept as 0, 3, which corresponding to that is 3, 0. If you set this one equal to 0, you get negative 3/2. So negative 3/2, 0, corresponding to 0, negative 3/2. So again, 0, 3 is the y-intercept for here. For the other one is 3, 0. You can check it out even here or here. For this one, if you set this one equal to 0, x becomes negative 3/2. So negative 3/2, 0 is the x-intercept of f of x. So 0, negative 3/2 is the y-intercept of its inverse. And I'm going to assume everybody can graph them easily. This is 0, 3. This is negative 3/2 means negative 1/2. Negative 1/2, 0. This is 3, 0. And this is 0, negative 3/2. So extremely simple. Find the inverse of a domain restricted function. Find the inverse of f of x equals x squared if x is larger than or equal to 0. The reason is because y equals x squared is not a one-to-one function. The restriction on the domain makes it a one-to-one. And we want to graph f and f inverse. So first replace f of x with y. So we're going to call this y, makes it easier. And therefore, we are going to interchange x and y. We're going to call this x, we're going to call this y. So x equals y squared. And we're going to write, so interchange x and y. And we're going to write y is larger than or equal to 0. Here's the reason. The moment you interchange x and y, you find the inverse. So x larger than or equal to 0 for f of x corresponds to y larger than or equal to 0 for its inverse. This is its inverse, but we will solve for y. So to solve for y, I hope you recognize y is plus minus square root of x. There are two answers. However, y must be positive, and you go with this square root of x. That's what you want to be careful when you want to solve for y. Okay, y is square root of x. What do we call this? F inverse. So f inverse is square root of x, and as you know, square root of x, x must be greater than or equal to 0. So just right here, if you want to discuss the domain and range, the domain for f, x is larger than or equal to 0. The range for that, because this is the domain of f inverse, is the range of this one, y is greater than or equal to 0. Okay, and you can have the domain and range for both of them as a result. Now, let's look at their composite function, f of f inverse. And again, f inverse of x, we said is square root of x. Domain of f, d representing the domain, r representing the range. Domain of f is range of f inverse, 0 to infinity. Domain of f, 0 to infinity. And that would be the range for f inverse. Domain of f inverse, we said x must be larger than or equal to 0. That's the range of f, 0 to infinity. It so happened both of them are 0 to infinity. Okay, that is not always the case. Okay. So f of f inverse, we are going to replace the x here with square root of x, and when you square it, you get x. How about f inverse of f of x? That is square root of x squared, because you are going to replace this x with x squared. Now, square root of x squared is equal to absolute value of x. However, the reason we know it's x, because x is greater than or equal to 0. You look at this one, remember, this x. X is greater than or equal to 0. So the answer is absolute value of x, which makes it x. It's important to understand this. Now, graphing is very simple. I'm not going to spend too much time on that. Plus, y equals f of x squared is like that. And since x is larger than or equal to 0, we only have the right side. And we know square root of x looks like this. And as you can see, they are inverse functions and symmetric with respect to the line y equals x. Again, remember, f of x equals x squared has this piece also, but x is greater than or equal to 0, and that makes a huge difference. We want to find the inverse of f of x, where f of x is 2x plus 1 over x minus 1. Needless to say, x can't be 1, right? The denominator can't be 0. And we want to graph them. First and foremost, we're going to replace f of x with y, so we're going to call this y because it makes life easier. The next step is to interchange x and y, so we're going to call this x, and this becomes 2y plus 1 over y minus 1. And the next step is to solve for y. So to solve for y, we do the cross product. X times y minus 1, 1 times 2y plus 1. And so the left side is xy minus x. Since we want to solve for y, we are going to move things around as follows. So 2y goes this way, becomes negative 2y. Negative x goes to the right, becomes positive x. And we are going to factor the y out from the left side. We get y times x minus 2. Divide both sides by x minus 2. So this is solving for y. Call it f inverse, so change the name to f inverse. F inverse of x becomes x plus 1 over x minus 2. Needless to say, x cannot be 2, everybody. X cannot be 2, right? In other words, right here, we should know the domain for f, x can't be 1. That would be the range for f inverse. That means y can't be 1 for this one. The domain for f inverse, x can't be 2. That means the range for f, y can't be 2. That's the idea. Now let's check by looking at f of f inverse or f inverse of f. We're going to look at one of them. For example, if we look at this one, in this function, we replace the x with x plus 1 over x minus 2. So in this function, replace this x and this x with x plus 1 over x minus 2. Therefore, we get 2 times this plus 1 over x plus 1 over x minus 2 minus 1. Now, this is a complex fraction. And the easiest way to do this, we're going to multiply the top and the bottom by x minus 2. Simplifying a complex fraction. When you multiply these two, x minus 2 goes away, and it becomes 2 times x plus 1. You multiply these two, you get plus 1 times x minus 2. When you multiply these two, you get x plus 1 because x minus 2 goes away, minus 1 times x minus 2. I'm assuming nobody has any problem with complex fractions. So one more time, you multiply these two, you get 2 times x plus 1. Multiply these two, 1 times x minus 2. You multiply these two, you get x plus 1 and x minus 2 goes away. These two minus 1 times x minus 2. So what do we have here? Two x plus 2 plus x minus 2. So we have 3x here. Over here, we have x plus 1 minus x plus 2. And the denominator is 3. 3x over 3 is x. We proved their composite function is x, so we don't have to worry about that. As far as graphing, I'm going to assume you know how to graph rational functions by now. And so what we are going to do, I'm going to show you the graph, and I want to compare the asymptotes. Remember, to graph this, you have to have a vertical asymptote, horizontal asymptote, intercepts, you know, you name it. So if you look at this one, the graph looks like this. Here's the horizontal asymptote. Here's the vertical asymptote. Y equals 2. Take a look at this one. Because the degree of the numerator and the denominator is the same, the leading terms take over. 2 over 1, so y equals 2. And x minus 1, that means x equals 1 is your vertical asymptote. Now, because x equals 1 is a vertical asymptote, for the other one, the horizontal asymptote must be y equals 1. And because y equals 2 is the horizontal asymptote, x equals 2 must be the vertical asymptote for the other one. So when we graph this one, clearly what I just mentioned, this one and this one, x equals 1, now y equals 1, because look, both of them have degree 1, so 1 over 1, y equals 1. And this one, if you set x minus 2 equal to 2, to x minus 2 equal to 0, you get x equals 2. So y equals to horizontal asymptote here, x equals to vertical asymptote for its inverse. So very straightforward, everybody. We want to continue finding an inverse of a function. Find the inverse of f of x equals x squared minus 2. If x is larger than or equal to 0, state the domain and range of f and f inverse and graph both. Again, notice y or f of x equals x squared minus 2 is not a one-to-one function. The restriction gives half of it, and therefore it makes it one-to-one function. That's why it's important to understand. So this is the domain for the function, which automatically makes it the range for the other function that we are going to find in a moment, the inverse function, okay? So x larger than or equal to 0 is the domain for this one. Y larger than or equal to 0 is the range. In other words, 0 to infinity is the range for the inverse. So number one, we're going to change the name to y because it makes it easier. Number two, we are going to interchange x and y. So this becomes x, this becomes y squared minus 2. Now, y is y larger than or equal to 0. When x is larger than or equal to 0, which is the domain of this function, then y is greater than or equal to 0, which is the range of this function, which is the inverse, as it was mentioned. And we are going to solve for y. To solve for y, x plus 2 is y squared. Therefore, y is plus minus square root of x plus 2. There are two answers. And because y is larger than or equal to 0, we just take the positive one. Just in case if this was less than or equal to 0, this would be less than or equal to 0, and we would take the negative one. Okay, so it's the inverse function for the other half. So we're going to change the y to f inverse. So f inverse of x is square root of x plus 2, where x, now this you know, x must be greater than or equal to negative 2, because to find the domain, you say x plus 2 larger than or equal to 0. So right away, you have the domain and range of everything. So here's the domain for f. Here's the range for f inverse. And now x is larger than or equal to negative 2. That means the range for f of x, y, must be larger than or equal to negative 2. Now let's look at the composite function. F of f inverse. So we are going to replace this x with this function. So we are going to put square root of x plus 2 quantity squared minus 2. And these two cancel each other, the square root, and raising it to the power of 2, which will result in x plus 2 minus 2, which is x. So they undo each other. So we looked at their composite function, and we proved that their composite function is x. So therefore, given that f of x is x squared minus 2, and f inverse is square root of x plus 2, the domain of this function was given as x greater than or equal to 0, that means 0 to infinity, which is the same as the range of f inverse, okay? The range of f inverse. On the other hand, x is larger than or equal to negative 2 is the domain of f inverse, which makes it the range of f of x. So domain of f inverse, or range of f is minus 2 to infinity. Now, if you were to graph it, again, this is y equals x squared shifted down by 2 units. And then we have the right side. And this one is y equals square root of x, because of plus 2 has been shifted to the left by 2 units. So again, this one, square root of x, shifted to the left by 2 units. And this one, x squared, coming down by 2 units. And just the right hand. As you can see, the point of intersection, if there is a point of intersection ever, it has to be on the line y equals x. And you can easily find it by simply setting the two equations equal and find the point of intersection. In other words, x squared minus 2 equals square root of x plus 2, and solve that.